So hello guys, I am again with a new chapter today, new topic I would say. The topic names is damped oscillation. It's an nearly you can say it's an JEE advanced or Olympiad topic. It doesn't come in exams like JEE mains. It comes in exams like NSCP, but it comes majorly in INPHO. It's a very good concept. I can just show it to you. It's so what is the meaning of damping? Okay, damping means influence within. So there is an oscillating system, right? This is oscillating about its mean position. So this pendulum just gets influenced within or upon by an effect of some force. It's called the damping force, and it has effect by reducing or preventing the oscillation of this pendulum. So I want to say just damping is just so an influence within which this oscillating system has a effect by reducing its oscillation, right? So a very important thing is damped oscillation, that in a system that has very small amount of damping, the period and the frequency remains constant. I wouldn't say this is fully constant, but we can assume it as constant. It's nearly constant, and same for as SHM. Okay, but one thing you can see, the amplitude will decrease over time, right? The amplitude will decrease over time. So if we write the differential equation of damped oscillation, it will be m d squared x by dt squared, which is force, right, plus kx. This is the restoring force which we have run. It's minus kx. At this side it comes when it's become plus kx, right? K is the let me write. So k by m root under is the omega's value, right? Angular frequency, plus b dx by dt. Dx by dt is bv. It's generally here b into v instantaneous. B is the damping factor or damping constant, and no, b is the damping constant, but b by 2m is alpha. This is the damping factor. So what I have talked about, damped oscillation is just an oscillation under the influence of a force that reduces or prevents the oscillation of a oscillating system. Okay, it just reduces the oscillation, and for a system that has small amount of damping, the frequency and the period remains constant. And this is the differential equation of the damped oscillation. Here b is the damping constant, b by 2m, alpha is the damping factor. Okay, sorry. So this is the form of the damped oscillation. This is the equation of the damped oscillation. Okay, and if I talk more about this, let us take e to the power RT be its solution of the differential form. Okay, So in SHM also we have learned that we takes a sin omega t as its general equation, and we just solve it in that equation, m d square x by dt square plus kx equals 10, and we just solve it and prove it whether it holds true or not. It holds true, so here also we will take e to the power rt as its solution. Okay, we're assuming the solution of this form. So this is obviously x of t is e to the power rt, dx by dt should be differentiating with respect to time, so 1 by e to the power rt, differentiating this, multiply differentiating this r, right? D square x by dt square, double differentiating the same function, we will get e to the power rt r square, right? Just put it in the equation of m d square x by dt square, e to the power rt into r square plus e to the power rt, and it was k into x, so k into e to the power rt plus dx by dt, b damping constant into e to the power rt into r equals 0. We can cancel out e to the power rt, e to the power rt cancels, m r square plus k plus b r equals 0. So this is what, this is a quadratic polynomial. Just use the Sridharacharya formula to get the value of r. R becomes minus b plus minus root under b square minus 4 m 4mk divide by m 2m. So this is the value of r in this for solution. So just see this derivation. I will write this down. Okay. So what it just what the equation we have got, it resembles a cosine curve oscillating in a, if we just take out the functions of the damped oscillation, it looks like this. The envelope would be a form of exponential form, which we have already got, and the oscillating function is a cosine curve, right? This is the envelope, this is the oscillating curve. Okay, so here alpha equals b by 2m, damping factor. This is the solution. So if we write all together, I am just rubbing this and writing. The solution looks like what we have got, e to the power rt, r's value we have got, so x of t equals a naught, so capital A naught e to the power minus b by 2m into t cos omega t plus phi, right? This type of format we will get. I can show you the graph. Actually the graph is like this. So the cosine curve's maximum is a naught, here it's minus a naught. So first this is t, 2t, 3t. Okay, I'm drawing this 4t, 5t, 6t, up to 60 I'm drawing. Okay, so it starts like this. It's at like 0.5t, this is 0.5t. It gets its minima. Okay, and it gets at maxima at t. Okay, you can just prove it, it's very easy. So sorry, pardon. The graph starts from here, reaches its minima, finds its maxima again. Okay, so to understand you all, I'm not just directly drawing the graph. Okay, let's just draw the coordinates. Sorry, here it's 0.50. It starts at e0. Draw the function, draw the envelope first. The function will be exponentially decreasing, right? This, take this also, this. The graph isn't ending, I'm giving. Okay, this is the envelope. Remember, it's minus a naught e to the power minus b by 2mt, and it's a naught e to the power minus b by 2mt, right? So now it oscillates between this, like this. So you can see it's an oscillating function, and this is the function actually. This is the cosine curve. This is the actual function. This is the envelope, and this is the curve, cosine curve in between the envelope. It's something like this, like we have read it, I think. Most probably you have read, like sine of 1 by x. So y equals to 1 by x graph you draw and just do the sine curve here, right? So it's like this, the envelope. So the main thing is here is about the damping constants. Okay, if I draw another curve, like I'm drawing the general curve for any, I'm just drawing 3 curves. Let me take one this. Okay, one as this and one as this. This graph represents an under damped graph. Here b squared is less than 2,4 mk. M is the mass, k is the constant, and b is the damping constant. Okay, this is the underdamped graph. This graph represents critically damped. Here b squares equals 4 mk. This is an underdamped, this is an overdamped graph. Here b square is greater than 4 mk. So this is only the terminology. This much is only needed for the iron PHU. Previous year questions had been asked on this, like they have told you to draw the graphs, and this is the graph actually. So one more thing I would like to say, and I'm writing it here. The angular frequency of this damped harmonic oscillation is omega naught square, which we get generally, minus b by 2m. Means, I'm telling you, this is the solution of this differential equation of damped oscillation. Means it's generally omega squared equals to omega naught squared minus alpha square, right? So I want to just say that omega square plus alpha square equals to omega naught square. It should be, don't you think? the damping reduces the oscillation, the reduces the angular frequency. So the final angular frequency will be alpha times additive of the angular frequency we have got, final angular frequency. So this is the all the concept about the damped oscillation. If we talk about this graph, the position versus time graph of these three systems consisting of a mass and a spring in a viscous fluid. I am talking about this. Here B is less than 4 mk. This is an underdamped graph. Why we would say this? Because the damping is small. So what happens in this case that the mass oscillates slowly losing its amplitude. Okay, it loses its amplitudes and it finally comes to rest. And the energy dissipated, important thing, the energy dissipated in damped oscillation is always done by non-conservative forces. And this is the b square equals to 4 mk is just the limiting case, nothing else. If the damping is very large, like in this graph, when it is critically damped, the mass doesn't oscillate when it is displaced. Okay, so what I am telling, nothing. If I leave this pendulum from here and the damping is b square greater than 4 mk, it will never oscillate, it will directly come to the equilibrium position. It is over damped, critical, it is over damped. And if b square equals to 4 mk, it will just lose the oscillation in just a short period of time, and in case of underdamped it will oscillate, like you can see in the graph also. Here it is maintaining a constant value, here it takes a large amount of time, take a short amount of time to just get the equilibrium position. So this was about our damped oscillation. Next day we will, next class maybe we will talk about forced oscillation and wave. Okay, so this was all about damped oscillation. I think I had tried to explain you how much I knew, so I think it is not enough, but you can solve questions at least from this. Okay, so this was all about. Thank you for watching my video. Good night.